I was waiting for somebody to introduce the session, but apparently there is nobody. So I'm Nicolas Rougier, and I will try to talk about interactive scientific visualization. And so I thank the organizer for giving me the opportunity to introduce this work. Well, actually, I'm working in neuroscience, and I will try to explain why I get involved in scientific visualization. So mainly I'm doing computational neuroscience, so I'm dealing with model of the brain, and so I'm using essentially Python. So there is a scientific stack in Python. So the main component are, of course, Python. There is also the NumPy and SciPy libraries that offer quite good numerical libraries. And now there is IPython that allows you to run Python within the browser. And there is a Matplotlib visualization library. So it's a very nice library, very versatile and beautiful. But the main problem is that it's kind of slow. So it's quite good if you need to produce a figure to put into a scientific article or to have some limited animation. But for when you have a very huge data, it's not usable anymore. So the Matplotlib library is based on the anti-grain geometry library, which is a C++ library, which output very beautiful graphics. And if you want to see the kind of graphics, there is this article, this is self-promotion about simple rules for better figures. So in this context, the easy solution was to look into OpenGL. So of course it's very fast, very powerful. So here's a small graphic about the power of the increasing power of graphic cards. So the video game industry is working for us. But it's fast, but mainly it's ugly, at least for scientific visualization. So it's ugly because we have no decent anti-aliasing. So I'm talking about aliasing at the level of curve or markers or text. There's only two image filters, that is native filters like nearest and linear. There is no native text handling, no markers, no arrow, no path, no curve. So it means if you want to do scientific visualization with OpenGL, you have to do all by yourself. So today there are some proprietary solutions. So one is only 2 years old. This is a GPU accelerated path rendering. It was made by Mark Kilgard and Jeff Bowles. So this is a closed source, but it seems to be quite powerful. And there is also an API. It's called OpenVG, but there is only a few implementation, and most of them are proprietary. So the idea is we'll try to fix all of this, and of course we'll do it freely. So if you look at the OpenGL framework in Python, there are already a lot of projects. So you have the different rendering frameworks, such as, so first, PyOpenGL. Those are the OpenGL bindings, so you can just start programming OpenGL. There's Piglet, which is more powerful, maybe, and there are also some other projects. And for visualization, you have, well, 6 main. Already there are these 2 main projects. So one is VTK. This is a well-known library in C, so it has been ported also to Python, so you can also use it. But it's not that easy, and it uses what I call the old OpenGL. And there is Mayavi 2, which is also quite powerful, but not so easy to use and install. And there were 4 other projects, so Gallery, Vispy, Glumpy, and PyQt Graph. And so last year we decided to join forces and to propose a new unified framework for doing scientific visualization in Python using OpenGL. So first decision was to what kind of API we want to choose. So this is a small history of OpenGL. So starting from 1.0 up to, so maybe now there is already the 4. I don't know, maybe 5 and 5, okay. And so we have to, first move was to choose one context. And we chose OpenGL ES. I will just explain why later. but mainly because it was a programmable pipeline, so as opposed to the fixed pipeline. So now today you find a lot of reference for learning OpenGL, but they are using the fixed pipeline. And so when you are using shaders, to name it, you have more powerful capacity. So the decision was made on OpenGL ES 2.0 because, okay, this is a pipeline for OpenGL 4.2, and you have like 2,000 constant and 1,000 function. So it's quite powerful, but it's quite complex to really exploit all the power. And OpenGL ES is only 350 constant and only a bunch of functions. So it's more tractable for us, and you can have your visualization on mobile platform or on WebGL because this is more or less the same. And so the whole idea of this framework is explained with this simple slide. So we have the raw data. So those can be data from physics, chemistry, or astrophysics, or neuroscience. And you want to push them on the GPU directly to just visualize them on the screen. So this is the ideal case, but from most of the time you have to prepare your data before sending them to the GPU. Then you can transform them on the GPU, and finally you can render them. Of course, the difficulty is to minimize this stage because in Python it will be rather slow. And the ideal case is where we have no baking at all. So this is an example. We have an array of maybe it's 20 by 20 scalar values, and we want to just send them to the GPU and obtain this visualization. So in such a case, we have the interpolation, colorization, leveling, gridding, scaling, lighting, aliasing. All is done on the GPU. So this means we can save CPU power for the simulation. So of course, this is the easy case, and we have more complex case where we have a lot of transformation or a lot of baking to be done before sending to the GPU. So this is, for example, the case for handling transparency. Even so, there are now new algorithms. So where do we start? Well, we first started with SVG API, and so the idea is to implement the very basic tools that we need for scientific visualization. So mainly we need text, of course. We need path. So path is for example, drawing a line plot. We need marker, so when you have, for example, a scatter plot to show some data. We want also arrows, so this is within the basic shapes. And we also want to have a high level of quality. So I will try to explain some of the technique we used, but not all of them. I won't have time. So for example, for the text rendering, in OpenGL, you have several methods to render text online, on the screen. So the first one, the historical one, is to use bitmap description of the glyph, and you just put it on the screen. So this is quite similar to the texture rendering, but it's without the aliasing. You have also line drawing, so you just give the point and you draw a line between the point. You have texture rendering, so you save your glyph, for example, using free type in a texture, and you use this texture to render the screen. More recently, there is a new and quite good technique. It's called sign distance fields. So instead of saving the ink information from the glyph, you will save the distance to the border of the glyph. So this takes the same size, and I will show you an example just after, but you can achieve a higher quality with only a single glyph in memory. So for any size, you use a single information. Last is vector rendering, and once again, there are new techniques that allows you to have a pixel-perfect rendering of any glyph with a very fast performance. So there are some mini review in this article, and this is where also I expose another mixed technique using texture rendering. So I talk about the anti-grain geometry library, and the author writes this article, so it's online, and he explains how to achieve better rendering for font on screen. And so I won't enter all the detail, but the idea is that you can have, using texture glyph, you can have sub-pixel positioning and kerning. You have a per pixel gamma correction, and you can use also sign distance field. So I will try a demo. Okay, so this is a rendering in OpenGL, and this is to show you the even at very small size, like maybe 7.5. I'm not sure if you can read it, but it's still quite readable. So of course, there are hinting, only vertical hinting, subpixel rendering, and subpixel positioning for both kerning and glyph position. And you can change, of course, all the parameters. So this was one of the first steps in the library. And the other techniques. So this is sign distance field. So we have only one glyph into GPU memory using those distance, and then we can zoom at very high level without too much artifact. So there are some problems. So for example, you can see here, it's not the actual shape, and those may be less rounded. But it's quite efficient and very, very fast. And so for scientific visualization in 3D or 2D, it's a very useful. And so even a very small size or very big one, well, not too big, you get nice rendering. So we were okay with the text. So next stage was to look at polylines. So I don't know if you're familiar with OpenGL, but it's well, before the programmable pipelines, there was a GL line width that allows to control the width of a line. Yeah, yeah. First, it's deprecated and it's just ugly. Ugly because you have no control over the join and the caps, and you are limited in the line width. And anyway, it doesn't exist anymore. For the dash pattern, you have only the steeple properties that allows you to do some kind of line steepling this way. Again, it has been deprecated, and it was also quite ugly. No control over dash and caps. So we tried to fix this. And because we have the shader, we can now really control how a line is drawn. So those are some examples of dash, stars, and some other curve. So it works in 3D and 2D. I won't give you all the detail, but all the detail are given in this this paper. So I can show you a small demo if it works. Yeah, so this is a tiger. So again, this is render in Python with only one GL call. We just send all the line information. And so maybe you can't see it yet, but those are dash line covering the, so this is only the line of the tiger. And we can try to zoom. And this is also animated. But at this time, the CPU is doing nothing. The GPU is handling all the dash patterns, so it's quite efficient from a Python point of view. So we just send the phase of the dash, and the GPU will just render the line correctly. So one important thing also in scientific visualization is image interpolation. And so as you may know, in OpenGL, you have only the linear interpolation and nearest interpolation. And indeed, there are a lot more that are useful. So again, we wanted to implement those filters. And there's a nice article in GPU Gem, so there's a lot of techniques. And they explain how to implement high quality filtering. And so we can have all the 16 filters here. And this is, again, this is real time, if I can find it. So you can explore your image and see what's the effect of the different filters. Again, this is done at the GPU level, so you just send the data, and you're done. So it's again, it's quite fast. And finally, I will finish with this part. So we need also like grids, markers, and arrows. So markers are really useful in such things as a scatter plot. So you just throw a bunch of markers to know where are your data. You can also have arrows to, for example, quiver plot to show you what is the shape of a vector field, for example, and of course we have grid. So for such markers and arrows, the GPU is really drawing the arrows and the markers. So previously with all OpenGL, you have to draw the shape of the arrows and to draw the tail of the arrows and to do all kind of things, and eventually also applying anti-aliasing. In such a case, this is a sprite, so point in OpenGL, you just throw a point, and then you write a shader to draw the arrow or to draw the marker. So for example, for the heart, so this is what the shader look like. So this is only a mathematical function describing the distance to the shape. Once we get this information, we can draw anti-alias markers of any shape. Of course, the difficulty is to find the proper function. So in this case, this is a disk with a disk and a square. And so we combine them with some kind of constructive geometry. And we do the same for grids. So in this example, this is only two triangles. We send them to the GPU, and we write the shader to draw the grid. So this is polar grid, but we have all kind of transformation. So this was only some examples, and of course we still have a lot of problems to solve. So one of the difficulties is shader composition. So because now we can draw markers, we can use different colors or color maps. We may want to have light or not, and so the user is in control of what he wants in the visualization. And so we have to find a way to put all this shader together to compile just in time and to render the scene. So level of details is well known in OpenGL. So if you are very far from a scene, you don't need to render all the scene because some details won't be seen. So I can show you a small example. So this is an example. We have a million dots. They are disk, anti-alias, and of course, because they are all together, maybe you are seeing only 100,000 dots. All of them, the other are just hidden by the front ones. But this is, again, quite fast for Python point of view. Also, we have to handle complex data transformation. So for example, in cartography, you have weird transformation of the Earth. So when you want to project the Earth on a plane, so you have all kind of different transformation, and we have to also to handle them. And last point, which is maybe the most difficult, because now we have Python within the web browser. So the browser is a client, the Python kernel is running on the CPU, and they are talking to each other. And now the difficulty is how do we enable to control the WebGL context from within the CPU side. It's not that easy. So just to conclude, and I will try to show some demos, that we can have with OpenGL, modern OpenGL, we can have the speed and quality. So again, this is some examples. We can have now 10 million points. It's only 1 FPS, but it's from time to time enough to get a sense of what is happening in your visualization. And this is some comparison between what we get in Matplotlib, which is again very beautiful, and we can get the same level of beauty in OpenGL. Of course, it requires a lot of work. And those are the different information and links. So it's a little spread everywhere. So the main project is called Vispy. So it lives at this address. You have a gallery. You have also Glumpy, which is my own playground for testing IDs. And you have all the code here. You can also try to go to this address. So those are shader toys where you can experiment different shader. So I can show you maybe one quick example. Oh, not connected. So I can show you another one. So for example, this is not a real simulation, but this is a spiral galaxy. So I just translated the source from somebody else. So in this case, we are only using a point. So you have the point element in OpenGL, and with different size, different level of transparency, and the simulation, you get this nice fake simulation of a spiral galaxy. And for the transformation, okay, I cannot connect. And this is it. So if you have any question, not one of those.
No questions? Okay, thank you.